All right, now that we have went ahead and looked at the derivation of the Taylor series and why this formula here is plausible or anything at all, we're just going to do a quick little mention of this Maclaurin series. The Maclaurin series is a Taylor series, but it is a Taylor series that is specifically centered at 0. So if your C value is 0, then you are free to call it a Maclaurin series, or you can say a Taylor series centered at 0. But why not go with a shorter, easier, more convenient name of a Maclaurin series? Why would this be relevant? Why does this get a special name? Why are there other special names? Like, what if we center our series at, you know, x equals 12? Does that have a special name? No, I mean, in all honesty, the Maclaurin series, the reason why it has this name is named after somebody who worked with them extensively. Like most things in math that are named after a person, it's either the person who invented that or who really spent a lot of time making that area of math relevant or important. But really, here, the reason why this would be really important and nice is when you have a series whose radius of convergence is infinite, then it technically doesn't really matter where you center the series, at least not in a theoretical point of view. It doesn't matter because the series converges no matter where its center is, and it converges for all real numbers no matter how far away from that center. And so it becomes very convenient to then just work with your series centered at 0 because then it simplifies dramatically. This term here, if you wanted to actually multiply it out, that would take, we'd have to expand this out and use the binomial theorem, and that would be a little bit exhaustive. Whereas if we just have the center of being 0, then there is no need to expand, and that's all we have. So that's very nice. So it's really a matter of convenience, and it's customary to work with series that have an infinite radius of convergence. It's customary to work with them being centered at 0. It just simplifies the algebra. All right. So example 1, determine the Maclaurin series for the function e to the x and find its radius and interval of convergence. So to find the Maclaurin series, we really just want to be using this formula here, or this formula up here, equivalently, just with x equals 0, or excuse me, c equals 0 plugged in for the center. So down here, what we're going to do is a practice that you have done in Calc 1 when you were determining the nth derivative. So we want to find a general expression for the nth derivative. So we're going to start off easy because we're going to be working with e to the x, and we know that e to the x, all of its derivatives are the same itself, e to the x. So the nth derivative expression is very easy. So normally what I would do here, if this were any other function, not just e to the x, what I would do is I'd create a little table, and I'd put n in the far column. I would put the nth derivative of x in the next column, and then I would put the nth derivative with our center value plugged in. So we would have, I'd start off with 0, so then the 0th derivative is just the original function. And then if I plug in my c value, I get e to the, also for us, our center value is 0, so I'll just fill this in and put 0 for our center value. So I'm just going to say c equals 0 here. So we have e to the 0, which is 1. And then we do this again. Now we take the first derivative of this function, which is again e to the x, plug in our center value, and get 1. And we keep doing this. And you can see that if our function were something other than e to the x, then all these expressions here would change. And then we would be tasked with finding some pattern, and we would have to then write down a general expression, which can be a little tricky at times, but you have practiced this in Calc 1. So for this example, it is a little bit boring because our derivatives are all the same, so we don't really need to do the table at all, but this is what we would more or less do. So for us, our function is e to the x, and since e to the x is its own derivative, that means that the nth derivative, no matter how many times we take the derivative, we get the same expression, e to the x, which means that when we plug in our center value of 0, we just get e to the 0, which is 1. So our Maclaurin series for e to the x centered at x equals 0. Remember, our Maclaurin series is the nth derivative evaluated at the center divided by n factorial times x minus our center to the nth power. Well, for us, this becomes, well, we found this numerator. That's equal to 1. So our numerator becomes 1. Our n factorial stays there. And then, since c is 0, we just have x to the n. So some people put the x to the n in the numerator. That's very common to see for this series in particular. So this right here is the Maclaurin series. For e to the x. So now what we want to do is determine the radius and interval of convergence. So always start with the radius, and then from there we'll find the interval. So for the radius of convergence, we will examine the limit as n goes to infinity. We're essentially performing the ratio test. The absolute value of a sub n plus 1 over a sub n. So a sub n plus 1 is x to the n plus 1 over n plus 1 factorial. And if we divide by a sub n, we're going to flip and multiply. So this will be n factorial over x to the n. Now, of course, x to the n plus 1 is just x to the n times x. N plus 1 factorial is n plus 1 times n factorial. So then we can see that the x sub n's cancel, not sub n's, the x to the n's cancel. And we're left with just an x. Our n factorials cancel, and we are left with just an n plus 1. So now the absolute values won't affect the n plus 1 at all, but they will affect the x. So this becomes the limit as n goes to infinity of the absolute value of x over n plus 1. And if we take a limit as n goes to infinity, we get 0. So the absolute value of x times 0. So since x is some fixed number, a fixed number times 0 is 0. So this means rho for the ratio test is less than 0. This is always less than 1. So this means no matter what the value of x is, we are going to have convergence. So if we always have convergence, no matter what x value is plugged in, that means we can deviate as far as we want to from the center and still maintain convergence. So this means our radius of convergence is infinite because we can go as far away from the center as we would like. So because our radius of convergence is infinite, this automatically implies that our interval of convergence is just the entire real number line. So radius of convergence is infinity, and the interval of convergence is the entire real number line. So you can use the symbol that is commonly used, or you can also write negative infinity to infinity.